In this video, we're going to look at another example of working integrals. An inverted circular cone with height 8 meters and base radius 4 meters. The tank is filled with water to a height of 6 meters. Find the work required to empty this tank by pumping all the water over the edge of the tank. The density of water is 1,000 kilograms per meter cubed. So we start by defining some variables. Y equals 0 is the bottom of the conical tank. Y equals 6 is the top water level of the conical tank. Y equals 8 is the top edge of the conical tank, or equivalently the height of the conical tank. The density of water is 1,000 kilograms per meter cubed. And the gravity, of course, is 9.8 meter per second squared. All right, so let's sketch a diagram and define some variables. So we have the height of this cone is y equals 8. And the goal here is to find a distance that every slice has to travel to the top. So you can see that this slice, this cross-sectional slice, which is horizontal, is perpendicular to the y-axis, and this is just a slice of water. And so how much distance does this slice have to travel to reach the top? Well, the distance from the top of the slice to the x-axis is y. The height of the cone is 8. So clearly the distance that this slice has to travel is 8 minus y. Notice that all these slices here have to travel 8 minus y. They all travel different distances depending on y. So the goal is to get the cross-sectional area of these slices as a function of y and find the work required to pump these slices over the top. Then the integral adds up all the work that's involved in pumping these slices to the top. All right, so let's start by defining some variables here. So we know that the tank is a circular cone. That means all horizontal slices are circular discs. All of these slices are circular discs that are perpendicular to the y-axis. We're going to add them up in the y direction. So what is the cross-sectional area of one of these discs? Cross-sectional area will be pi times radius squared. What is the radius? The radius is just x because we set this up on a coordinate system. This is x, this is the radius. So we have pi times x squared. So this is the cross-sectional area of one of these slices. So now what is the differential volume? The differential volume is a of y, cross-sectional area, times dy. Essentially what we have is a cylinder. So here is x, the radius of this top circle. Here's dy, the height of this cylinder. So you can see how the differential volume is going to be pi x squared, the cross-sectional area, times the height of the cylinder times dy. So we get pi x squared times dy. Now we can't have x and y here because the integration is with respect to y. We're integrating in the y direction because the slices are perpendicular to the y-axis. So we have to get x in terms of y. How can we do that? Well, we can do that by applying similar triangles. Ratio of corresponding sides are equal. So what we have is this triangle, this smaller triangle here. So there's x divided by y, and this larger triangle here, 4 divided by the height of this cone. Let me split up these triangles just so it's more clear. So here is a smaller triangle, right angle triangle. This is x, this is y. Then the larger one this is 4 here, the top radius. And let me fix that. This is 4. And then the height is 8. So ratio of corresponding sides are equal. So we get x over y is equal to 4 over 8. Application of similar triangles to express x in terms of y. If you solve for x in terms of y, we get x is equal to 1/2 y. Differential volume is equal to pi x squared dy, cross-sectional area times the change in height times dy. This is equal to pi times 1/2 y all squared times dy. If we simplify this, dv is equal to pi over 4 y squared dy. This is the volume of one of these discs that has to be transported to the top to be pumped over the top. This is the volume of a thin disc of water. Let's draw that. So basically we have this thin disc like so. So here's the top radius, which is x, which we defined in terms of y, 1/2 y. This is the height of this disk. So differential volume is equal to pi times radius squared. The radius is x, 1/2 y, all squared dy. And we simplify this, we got pi over 4 y squared dy. So this is the volume of one of these disks. All right, so we have dv is equal to pi over 4 y squared dy, the volume of one of these disks, volume of thin disk of water. Now let's find dm, the change in mass. The mass of one of these cylindrical disks of water. This is going to be density times differential volume. So we get pi over 4 times y squared times the density of water, which is 1,000 kilogram per meter cubed, times dy. This is the mass of a thin slice of water. Now what about df, the change in force? This is g times df, gravity times the change in mass. So we get pi over 4 times y squared times 1,000 times gravity, that's 9.8, times dy. Now this is very important. So this df represents the force needed to overcome gravity acting on the mass of water in this thin circular disk of water at height y. Let's find dw, the work required to pump this slice of water over the top. That's going to be force times distance. The distance we found to be 8 minus y times the change in force df. So we have pi over 4 times y squared times 1,000 times 9.8 times the distance, which is 8 minus y, times dy. So this represents the work required to pump out this thin cylindrical disk of water over the edge of the conical tank, 8 minus y meters. All right, so now let's set up a definite integral and find the work required. So differential w, we found it to be pi over 4 times y squared times 1,000 times 9.8, gravity, times the distance traveled is 8 minus y, dy. So just to break it down, this part is cross-sectional area as a function of y. This part is the density of water. This part is gravity, g, and this part is distance. All right, so the work is going to be the integral from 0, y equals 0, to y equals 6, not 8. It has to be 6. We're going to talk more about that. So the reason, of course, is because the cone is only filled up to y equals 6. That's where the water is, from here to here. The cone is filled up to here from y equals 0 to y equals 6. All right, so now that's dw, and the work is going to be integral from 0 to 6, pi over 4, times 1,000, times 9.8 times gravity, times y squared, times 8 minus y, dy. Now all of these are constants. We can just push them out of the integral. So the work is going to be equal to pi over 4, constants can pass right through the integral, times 1,000, times 9.8, integral from 0 to 6, y squared, times 8 minus y, dy. If we multiply all these numbers, we're going to get the work is equal to 2450 times pi, integral from 0 to 6. Let's multiply y squared through, and we get 8y squared minus y cubed. And this is a simple integral to do, dy. So the work is going to be equal to, 2450 pi. And if we integrate this, we get 8y cubed. Reversing the power rule, divide by 3. And what is the antiderivative of y cubed? Add 1 to the exponent, divide by the same. We get y to the 4, divide by 4. And use the fundamental theorem of calculus to solve this. All right, so what we have is, here is the work equation. And we need to solve this using FTC, fundamental theorem of calculus. So let's put the upper limit in. We get 2450 pi. Now, plugging y equals 6, we get 8 times 6 cubed, divide by 3, minus 6 to the 4th, divide by 4, minus, plug 0 in, 0 cubed is 0, minus 0 to the 4th, that's 0, that's all 0. And if we simplify this, we get volume is equal to 2450 pi times 6912 minus 3888, taking common denominators, doing some algebra, divide by 12, and simplify further, we get 2450 pi times 3024, divide by 12. So we get 2450 times 252 times pi joules of work needed. Let's simplify a little bit more. The work required is 617400 pi joules. If we decimalize this, we get 1939619.3. 1939619.3 joules. Now, let's talk about the limits of integration. So there's an important note here. We integrated from y equals 0 to y equals 6, not from y equals 0 to y equals 8. That would have been wrong. So let's talk about that. We integrate from y equals 0 to y equals 6 because the conical tank is only filled up with water to a height of 6 meters. Even though the height of the entire conical tank is 8 meters, so the key concept here is only integrate y values up to filled water levels or filled fluid levels. And in this case, the 8-meter conical tank is only filled up to a height of 6 meters with water. All right, thanks.